I'm David Kamensky. I'm from the University of Virginia, and I've been working here at Ohio Wesleyan with Dr. Krauss on numerical relativity and black hole mergers. The goal of this project in the long term is to model black hole mergers using computer simulations, and specifically to include the effects of massive accretion disks on the black holes, because previous simulations that have been done in this area have either been only in 2D or have not included accretion disks, and they've come up with some results such as kicks after the collisions that would suggest things like the impossibility of supermassive black holes remaining in galactic centers, which we know empirically is not the case. So the simulation method we've chosen to start with is what's known as smooth particle hydrodynamics. And what that does is, instead of the traditional grid-based methods of fluid simulation, it instead discretizes fluid elements themselves and sort of traces them independent of any coordinate system. And it's not quite like modeling individual molecules, because you're using many, many orders of magnitude fewer than if you were actually trying to model the effects of individual fluid particles. But what it does is use a little bit of mathematical trickery to smooth out the particles that are representing these fluid elements. And in particular, we've been working with an existing code for this smooth particle hydrodynamics known as Gadget 2, which has been in the works for quite some time, and the latest version was released in 2005 by Volker Springel, who works in Germany. And what we've had the first challenge we have to face in using this code is to generate initial conditions. That is, as I was saying, it takes in the positions and velocities of many particles, and these have to be generated by the user. In other words, Gadget 2 it comes without any batteries included or anything. So we had to create our own homegrown solution to generate these positions and velocities, evolving these particles through a series of time steps. And so this initial conditions generator that we've been working on creating is intended to be a very versatile solution, because it would be fairly easy to come up with sort of just a screen full of code that spits out one particular distribution or another. But if you end up wanting to try a whole lot of different situations, you're going to have a lot of redundant code if you code each one independently from scratch every time you want to generate a file full of positions and velocities. So what we've done is tried to take an object-oriented approach, figure out sort of the common threads between generation of different distributions, and then bundled it all into one solution that's very easy to add new distributions, new functionality to. And the choice of language initially was C++, and there was a pre-existing solution that I spent much of the summer optimizing to increase the performance of it. Because when you're dealing with on the order of 10 to the 6 particles, using an order n squared algorithm is really just not practicable, and you really want to try to cut down the efficiency orders of everything you're using. And one way I've done that is to go through and use the C++ standard template libraries, which have very efficient sorting algorithms, for instance, because one of the routines in the initial conditions generator was Keplerian stabilization, and to include the central mass that's within a particle's orbit, you want to sort them all so you can just step through and keep increasing the central mass as you go along. And using bubble sort, for instance, is completely out of the question when you have millions of particles that you're trying to do this for. And another important tool that I just sort of did most of my spare time was a visualization that was helpful in debugging. And what it does is it plots the positions of all the particles in a distribution so that you can figure out that, whoops, the attempt at a circular disk that I made in fact has some error in the inequalities that's making it do a square, and that's really painfully obvious in a visual depiction of it, not so much when you have just a big list of numbers, and definitely not so much in the binary file. And then the idea is, after we finish this initial conditions generator, we will go on to modifying Gadget itself, which is something else that I spent some time working on this summer, but so far the only successful modification I've made to Gadget is causing it to have a segmentation fault. But I've made some progress in developing a promising route for adding sync particles to the program that will pluck other particles out of memory when they fall within an accretion radius and then meet some certain conditions in terms of their relative velocities. But that proves fairly difficult just due to the structure of Gadget 2's code, which is all in C, very procedural, uses a lot of global variables, and so it's difficult to go in and add your own stuff to it. And another sort of project that's come up recently and will probably continue to go on is the development of a Python module for generating initial conditions that will make it even more easy for the user to extend and modify the initial conditions generation process, more so than the C++ version, because the Python module can just be imported into a script, and it almost removes the distinction between code the users created themselves and code that was anticipated by the developers.